Welcome everyone. So this is our 83rd or 84th live stream geometry. I think it might be our 84th. And we have 5 other people here with us. And today I'm going to go over problems from various team selection tests in 2022. So I'm taking a couple from Iran, one from Israel. Johanna says it's the 94th. So one from Israel, one from Indonesia, and I took a problem from a mock Vietnamese Math Olympiad that was sent to me by Khan. So this will be a change from the usual problems from the Discord Geometry Olympiad. And so with that, let's get started. So if you're watching and you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So I'm sharing my screen. This is the first problem we'll go over from the Iran team selection test. And I'm using a new computer today, so we'll see how that works. Let me just make the problem statement a little easier to read. So that, there we go. All right, so we have a cyclic quad, and O is the circumcenter, A, B, C, D, and we draw the intersection of the diagonals. So I'm going to draw point D in just a second. Let's draw the sides and diagonals. And then we draw the midpoints of A, D, and BC. All right. This is P, and M and N are the midpoints. So obviously OM and ON are perpendicular to the sides. Let's make O and M a little farther away. So maybe like that. And I see Hakan just joined. So this will be M. And this will be N. Then we draw the circumcircles of ABP, BCP, and OMN. And we try to see where the circumcircle of OMN meets those two. Okay. Let's see if I can make this look a little easier. E, I'm not sure what E is. Oh, I didn't draw that circle right. Okay, so sorry, one sec. So it should be DPA, BPC, and OMN. So I think it's probably worth drawing the intersection of BC and AD because that'll lie on this circle. So why don't I first draw that in so we can get that in the diagram. So we have this and this, and they should intersect on that circle because we have 2 right angles here through O. I wonder if I want to make O and M farther apart, how should I do that? We're not that close together, but yeah, that looks good. Okay, and it looks like these concur. Is that obvious? Is that just some Mikel point thing that says that these concur?
Yeah.
Okay. And I got to rename them. So let's see. It says the intersection point. Okay, so E and F are really the same point. Well, which is not on the arc APD. Okay, so no, I have to draw these 2. Okay, so these are really E and F. So I'm going to rename a couple things. So yeah, this problem looks like it might be like trivial by Mikkel's stuff, but we'll see. F, we'll call this G. And we'll call this one K. So we just want to show that this is an KO is an angle bisector of EKF.
I think we should invert around ABCD.
Okay.
That's okay.
All right.
We have many circles, and the condition OF equals OE is very good under inversion. You just have to prove that OF prime is OE prime. So
okay. All right. So
it seems like MP and E are collinear. I haven't proven it yet.
But if M, okay, and MP and E and MP and F, okay. And then we could try inversion. Let's see why that might be true. Is this a, I don't think this is a symmedian, is it? PF and PE? Maybe they are symmedians. Yeah, it's a symmedian. Is that, oh, so, well, yeah, that would be true. It's equivalent to showing PF is a symmedian, which is the same as showing that APDF is harmonic. Okay. So is there something we could project through to show APDF is harmonic? Hey, Melik, thanks for joining. So we just started our first problem. So I'm taking problems from Iran, from a bunch of different team selection tests in 2022. Okay, so APDF, what can we project through to show that it's harmonic? Can we project through P? Let's see. So APDF, yeah, there's got to be a way to show that's harmonic. Basically, we want to show the tangents at P and F concur, and I wonder if they also concur at K. No. Okay. It almost looks like this. I think it's true that this tangent line is parallel to BC. I think that's true by like Rhimes' theorem. Yeah. So this tangent line through P is parallel to BC. So maybe that might help.
Inverted problem looks very nice. I can just state how it would be. You would intersect AB and CD.
Okay. I'll make some room for that. Just a moment. Let me make this. Yeah, I could shrink the figure, or I could make this one row longer. I think that's good. Okay. So these will intersect at point H. And do you want to invert about H with radius HP?
No.
Okay.
No, we invert around ABCD, that circle. But instead of like explaining the whole process of inversion, I will just say what the inverted problem is and what we need to prove it then. So HP is, you draw line HP.
Right.
And you intersect that line with circles HBC.
HBC.
Yeah, HBC. HBC, not P.
Oh, sorry.
And also with HAD. So like those two Michael circles.
Okay.
And you want to show that OI is equal to OJ.
Interesting. So it becomes a much simpler problem.
Yeah.
And it looks like, yeah, it's probably obvious that HP passes through the radical axis of these two, right? Just because it has the same power with respect to them.
Yeah, I think so.
Okay, so let's assume that all the things that look like they concur do. And then we want to show OI equals OJ. So yeah, I could hide a bunch of stuff. So yeah, for now, I'll just hide everything that's not that. HBC. Do we need this point E? I don't think so. Yeah, we don't need M and N if that's the case. Oops. We don't need this circle.
In whole, we need just 3 circles to draw the inverted problem.
Yeah. So all we need is that, and we need to show OI equals OJ. Okay. It still might be useful to extend these two, actually. Let's see. Are there any congruent? Let's see. Is OIQ congruent to OJL?
It must be if the problem were true.
Okay.
An equivalent thing to prove is that IQ is JL.
Yeah. So I and J, we want to show they have the same power with respect to this circle. Interesting. Yeah. Wonder if we can use the power ratio lemma, but we need one other circle through B, C, and P. For any line passing through H, which can be proven by the ratio -1 power circle. Okay, so any line. Okay, so you're saying even if it was a different line, like this one, it would still be true. That QI equals JL. Okay, so if we could show it for any other line, like if we could show it for this line, or even, let's think about this. Yeah, we could show it, if we could show it for any line, then it's true for this line. So maybe the line through H and O, is it Is that one obvious? Yeah. Maybe the perpendicular from H to BC? Not sure. Or maybe the midpoint of arc BC. Interesting. So yeah, I think Khan is just saying, like, once we prove it for one line, then it's proven for this line. Like, so basically for this line, if we could show that RS equals TU, then we can apply the power ratio lemma and show that QI equals JL. So basically, yeah, when he says -1 power circle,
can I do an explanation?
oh, what?
Can I do an explanation?
Yeah.
Like, could you define the point, the intersection of circle HBC and circle HID? Like the
Yes.
Nikolai point.
Yes.
Like the circle passing through H, V and O, like that circle is -1 power ratio circle with respect to HBC and HID. So like if you take any point on that circle, the ratio of its power to both circles is -1.
Okay.
So like because it passes through the midpoints of AB and CD.
Okay. So
Yeah,
that-
makes sense by power ratio lemma.
So then you intersect line HR with this circle.
okay.
So since for any point on this line, no, on the circle, the power ratio is -1, it must hold that RI1 is equal to A1T by power.
Yeah, and then this is perpendicular, so it follows that SR equals TU.
Yeah.
Interesting. I like that. Okay.
Very nice.
So okay, so yeah, that basically solves the whole problem. So okay, so I'm gonna write this out. So yeah, first we have to do the inversion, which takes it to the new problem. Call this Z. Whoops. No, let me call it, sorry, that was already Z. Let me call it Y. All right, so I'm going to unhide the original problem, and then we can show how inversion changes it to the new problem. Let's see, so we have this circle, M and N. Okay, and then we have this circle, E and F. That's E, F is off the screen, so I'll move it up so we can see point F. That's point F. Call that G.
We don't need G.
We don't need G. Okay. All right.
Okay. So we invert around the circle ABCD.
Okay.
Point N goes to the intersection of tangents at B and C to
Okay.
ABCD. That is very self-explanatory.
Yeah.
And now probably the most like heavy part of this inversion is that those two concur on HP, and that is simple actually by Pascal's theorem.
Okay. So
I will write the proper Pascal's theorem for that.
okay.
And then you will do the same thing for the other two tangents at A and D. And basically circle OMN would invert to align HP.
Right.
You don't need to draw them, you can just
Just say it.
yeah. You drew in the wrong tangent, that's why it is not doesn't look linear there.
The wrong circle. Okay. I wonder if our Y, O, and K. No, I don't think they are collinear. I was gonna say if that were true, I would probably make an easy solution. Okay, so N goes to R under the invert. Oh, they are. Interesting. So yeah, I think that might. But yeah, let's keep doing this. So N goes to R, and then M goes to that other point that lies on HL. But yeah, I think OY, AD, and BC concur. I think by the radical axis theorem, since this is cyclic right here, and let's see, is actually maybe it's not that obvious. Oh, AYOD is cyclic. BYOC is cyclic, and this is cyclic. So yeah, by the radical axis theorem, they would concur. All right.
And for the rest of inversion, intersection of OMN and BPC, that is also quite easy just because of the fact that because of the Mikkel point, I mean, a very standard stuff, that P inverts to V here in this diagram, and so BPC inverts to BHC.
BPC inverts to BHC.
Yeah.
Because P inverts to V.
Yeah. And after that, you invert just APD in the same manner, and we get that problem.
Okay. All right. So let's write it up here. Invert about ABCD. Center O. N goes to R. Okay, so N goes to the intersection. It's like R of the tangents B and C, and then we can apply Pascal's theorem, like you said. And show that lies on. So I wonder if there's a can we use poles and polars? So like R. Yeah, probably if we intersected these two, that would probably just be a pole and polar thing. But yeah, Pascal is good, so I'll write that out. So by Pascal on R lies on HL. So yeah, L isn't defined in the problem, but okay. And then define S similarly. We'll say similarly, let S equal AA intersect DB. Then S is on. So we have BPC goes to HBC. BPC to HPC and APD to HPD. Well, no, I didn't say something right. BPC to HBC and HAB. By Miquel theory. Just say by Miquel for now. Okay, so the problem then reduces to showing that OI is, so basically it therefore takes F to E. I'm sorry, it takes E to I and F to J. HL intersect HBC. Takes J to, no, it takes F to J, which is HL intersect HAB. Now, the problem reduces to showing OI equals OJ. And then we use, so let W and Z be the midpoints of A, B, and CD. Then WOZ is cyclic. I'll say by right angles. All right. Let HWOZ intersect HL at Y. Okay, so I'll say cyclic by right angles and all points on it have points, I don't know, should I say, all points t on it have power of t with respect to HAD and HBC. So equal to -1. Okay. So then we would have YQ equals YL by the above power lemma. We have YQ equals YL. And that implies that QI equals QJ, well, if YQ equals, sorry, YI equals YJ, and that implies OI equals OJ. Which solves the problem. All right. So the one thing that we kind of skipped over a little bit here is this step. I might just leave that for the viewers, that it takes BPC to HBC. Because like you said, it takes P to V. So yeah, but yeah, this is a fun one. Yeah, inversion solves a lot of stuff really fast. All right, so I'll move on to the next problem just because I know we're gonna have some harder ones today. This one was sent to me by Khan. So ABC is a triangle, and O, we have the circumcircle and 9-point circle. All right, I'm going to draw the 9-point circle in the end because eventually we're going to want to show these three things meet on the 9-point circle. So we draw the circumcircle, and we draw the centroid and the orthocenter. So I'm going to use GeoGebra's tool to do that. I think the centroid is triangle center 1. Is that right? No, that's the in-center. I guess 2 is the centroid, right? And the orthocenter is triangle center 4. I don't even know if that was right. Let's see. I'm starting to think it might not be. Oh yeah, that looks like the centroid. Yes. Okay. So yeah, I could draw, let me draw the center of the circle just so that we have the Euler line. Call it O. So here's the Euler line. HG is 2GO. I don't know if it's worth drawing all. Yeah, I'll draw all the midpoints just because we're looking at the 9-point center. Okay, D is the foot of the altitude from A to BC. Okay, so it's probably, yeah, I'll draw the 9-point circle right now just to make it easier to draw the rest. But really this should be, we can call these M, N, and P. And this will be D, E, and F. Okay, I think that looks good. The tangents at O at B and C meet at point T, and AG meets that circle at K. So, okay, so AG is the median. Do we even use point G, or do we just use that the median intersects it at K? Yeah, I don't know if it's necessary to draw G. I don't think it is. So
Yeah, they want us to prove that GQ meets the other two lines on the 9-point circle.
oh, you're right. Good point. So we do need G. Okay, so the two tangents, they meet at a point. If I make this too tall, then these points get really close. So let me see what I can do here. Maybe shrink it and make it shorter, but just give it more room. So yeah, I wish these would be a little farther apart. Let's see. Maybe something like that. I think that looks good. So once I close this, it'll make more room. Okay. Q is such that AQH is 90. I think we need to know a little more about Q, right? Is there anything else?
Wait, I'm reading the problem again.
Okay.
It seems like the proposer, I think I translated it right, but wait, let me think about it.
Okay, so this should be T. Yeah, we might be able to use the problem itself to figure out, because TD, HK, and GQ we want to show they meet on the circle. So let's see. So Q. AQH. So this would be Q. So maybe Q is where, let's see, QH. Well, okay. Basically, we want to see where that meets this circle, AFHE. Oh, so it looks like this point. Is that the 9-point center? Let's see.
No, and that point is absolutely irrelevant. It is just the perpendicular foot of perpendicular from A to Euler line.
Okay.
And also O is not important, as I see.
Yeah, I think the problem states that Q is the intersection of the altitude from A onto OH.
Okay. So from A onto OH. So that's just Q. So Q is the altitude from A to OH.
Wait, so it doesn't make any sense because then GQ is just the Euler line. Is it?
Oh yeah. What was I doing before? GQ.
It looks like the correct point Q maybe lies on the actual altitude of ABC through A. Oh no, it doesn't actually.
Who is on the circumcircle? Isn't that obvious?
HK.
Q can also be on HM. Like it could be intersection of HM circumcircle of ABC.
HM. Well, and GQ. Okay, so Q.
Like it's a Q point. It's called, I think.
Okay, so yeah, Q I think should be the AQ point. Yeah, I think you're right. Okay. So yeah, Q is basically the Q point. And so yeah, it's just where HM and these two circles all concur. So yeah, we could draw HM and Q, and of course that also this line also passes through the antipode of A. Might as well draw that. So let me do a couple of things here. So this is the antipode of A. These all lie on a line. And yeah, we want to show that these meet on the 9-point circle and that QG also passes through it. Okay. I don't know if it's worth drawing this point and this point. I'm just going to do it just in case we need it. Oops.
Never heard of the Q point. Does anyone have any resources on that?
So the Q.
Yeah, Q point is a point which has many properties.
Yeah, the Q point, it's just where the circle with diameter AH meets the circumcircle of ABC. And then QHM and the antipode of A are collinear.
It sounds kind of similar to the Humpty point, but like not really.
It is a Humpty point actually. So it's kind of like a Humpty point of triangle BHC, I think. Let me think about it. Yeah. Well,
Okay.
actually, is that correct? Let me think about that.
It is.
Okay. Yeah.
But I think the most common property is that QHM and A prime is collinear. Yeah, and mostly we use that.
Yeah.
And are there any good handouts on that? Or any?
So there's this packet written by someone who was previously on my channel called I3435. I don't know his actual name, but that's like the name he used on the internet.
American configurations?
Yeah, yeah, that one.
Oh, it's in there?
Yeah, he
Oh,
discussed
okay.
it
Okay, thank you.
a little bit, yeah. American geometry configurations. That's a joke, but yeah. Okay. All right. So yeah, we want to show that PD and HK meet on the circle, and then we want to show that Q, I, and G are collinear. Let me draw the altitude.
Maybe we can draw MF and ME because the homothety takes EF to BC, takes T to M.
It takes T to M. So
Because
basically
MF
MF and ME are tangent.
Yeah.
It-
Yeah. And if we intersect QT with the circumcircle of ABC, yeah, it's gonna lie on the line AD.
Okay.
So maybe
I didn't know that. Interesting.
it's
Yeah, it's
basically
kind of
the
simple.
homotopy. Yeah.
It's very simple, just harmonic bundles.
Okay.
Yeah, same thing. Yeah, I was gonna say that.
All right. So MEF is like similar to TCB. Obviously, OM and T are collinear. But Melek, you were saying something about homotopy. So like a homotopy about some point takes MEF to TCB.
Yeah. Homotopy at Q takes the quadrilateral QBSC to the QFHE, I guess.
FHE. Oh, I think you mean a spiral similarity, right?
Yes, and not homotopy. Yes.
That's all good.
I'm sorry.
Yeah. All right. Okay. Okay, so let's first try to show that these two intersect. Maybe we could first show that HK and TD intersect on this circle and then try to show QI and G are collinear. I don't know if that's the best order to do it. I'll try that.
I agree. We should do that. I agree. We should do that because QG is kind of weird line, so we shouldn't. Yeah, we'll prove it later.
Prove that last. Okay. So TD corresponds to HM and that spiral similarity. That's what Melek just said. Or no, that would be TS and HM correspond. Think. Yeah, basically I want to try to calculate the angle between HK and BT. So HK. What do I want to show that's equal to? I don't know if this point's going to help. Maybe AR is collinear with U. I'm not sure if that's true. It might be. No, it's not true. Sorry. All right. Yeah, HK trying to think what HK means. I haven't, like, I've seen HA prime, but HK I haven't seen in too many problems. So we know AK and AT are isogonal. I wonder if, let me check this. Oops. Let me see if these are isogonal. K, A prime H, and S, H, T. Those are not isogonal. Okay, so the angle of that spiral similarity, that would be like the angle between QM and QT, or the angle between QB and QF. Let's think about that.
I think I have some okay progress on this.
Okay.
So here I defined that point. That point we need to prove is on the other line. I mean, other circle, 9-point circle.
Yeah.
I define it as TD intersection 9-point circle. That just looks like the easiest definition of them all.
Okay.
And there are two steps to prove that I, H, and K are collinear, and the other one is that G, G, I, and Q are collinear.
Okay.
And I think that inversion is the best way to do, like, go here, because if we invert at H with radius HD times HA, and we do a negative inversion, that just means that we flip everything again by H.
Okay.
Then A would go to A and D swap, and F and C swap, B and D swap. So we have like triangle ABC, it like swaps to DEF.
Yes.
And basically, we would need to show that I, H, and K are collinear. So I and K would swap under this inversion, which means that IDKA should be cyclic. We don't know that.
Okay.
We don't know that, but we need to prove that. And it may be sufficient, yeah, but that's something we should strive to prove. And also, I was working a bit of the other thing, and that is this inversion takes Q to M. That is also very nice. Just because AQDM is cyclic, that is quite obvious just by 90-degree angles.
Okay.
So if QI and G were collinear, then Q would go to M, I would, let's say for now, go to K, and G would go to, let's for now say just some point on Euler line. then we would need to show that HMK and that point is cyclic.
Okay, whatever G inverts to.
Yeah, but also because of this inversion, it will just that point on the Euler line, draw that circle. That is good.
Okay.
That point would also lie on circle AGD.
Okay. So that would,
yeah.
interesting.
So we would basically, for that part, need to show that AGD and HMK, that one intersection point lies on Euler line. And moreover, I found another thing, which also I didn't prove, about this circle HMK, but that looks useful. Intersect AD with that circle HMK.
Okay.
Then VT should be parallel to BC.
Interesting. Okay. So you haven't proven that VT is parallel, but that would be one of the consequences, right?
No, don't know why it is parallel for now,
Okay.
but doesn't look hard to prove.
Yeah. So HMK and ADG. So we let HMK and ADG intersect at U, and we want to show that U lies on the Euler line. There's also another point of intersection here. So yeah, we want to show one of the two lies on the Euler line. Yeah, the HMK thing, like showing VT is parallel, yeah, it feels like that shouldn't be that hard. Let's see if we can do that. So OM times, or TM times TO is TB squared. So maybe we could use that somehow. Maybe it's a little harder than I thought. So if we show OH and U are collinear, that's equivalent to IH and K being collinear, right? All right. Yeah, let's see if there's anything special about U.
Another thing I just discovered is that Q, I, M, and K are cyclic.
Q, I, M, K. And it looks like T's on that also.
Oh yeah. So that one looks like a crucial cyclic quadrilateral.
Yeah. So yeah, this would be a diameter of it. Or TW would be a diameter. Maybe we could prove it that way. Let's see. Is this a right angle right here? No. 1 second, guys. I'll be right back. All right, I am back. Okay. So yeah, if we can show U lies on OH, then that's the same as showing I, H, and K are collinear. Maybe we could use like the radical axis theorem somehow. But yeah, we'd have to find another radical axis that it utilize on.
How did we define point V?
V, we define it as where AB intersects the circumcircle of HMK.
Okay.
But yeah, we think that TV is parallel to BC, but we haven't proven it yet.
I think I proved that Q, M, K, and T are cyclic.
Oh, you've proven that this is cyclic right here?
Yeah, but not all 5 points, since I lying on that circle is equivalent to showing I, H, and K are collinear.
Okay.
That I proved by an angle chase, I think. I mean, I didn't finish it, but everything looks like we can find those angles, and yeah.
Okay.
Basically, I basically proved that TQM is equal to 180 minus MKT.
Okay.
And we use the fact that K would be like parallel Q and K, and the median thing point or circle would make parallel to BC. I didn't explain properly.
Oh, the median point. Yeah, that's
Yeah,
obvious. Yeah.
So TK would pass it, if you intersect TK with circumcircle again, it would make a parallel line with A.
Okay.
And that's how we get angle MKT.
All right.
And also we just use for TQM, we use the fact that QS is median and QM is median. And then we can calculate angles.
Okay. So that's how you show that QMKT is cyclic.
Yeah.
All right. So
So,
maybe we could. Oh, I'm sorry. Go on.
Is QF and K collinear?
Q, H, M, and A prime are.
QF and K. Because if it is, then we just have to use have to prove A, I, D, and K are concyclic.
Okay. I don't.
Oh,
Yeah, it's very, very close, but
okay.
so. All right. And AWA prime S is a rectangle. AW is tangent to this circle. So maybe we should define I to be the intersection of these two circles, and then we could show that TIL.
No, I don't like that.
You don't like
I
that?
think the I definition of I is good. Also, using this QMKT cyclic, now we can show that HMK and V is cyclic.
Interesting.
But yeah, because HMA, angle HMA is QTK, which is STK. And now we just prove that SVTK is cyclic, which is, I believe, very easy, just by 90-degree angles.
Okay.
And STK is then SVK, and that's it for that.
But do we know that SVT is 90? Like, do we show VT's parallel to?
Okay, it just depends on how we define. In this case, we define it as the intersection of parallel through T to BC. That is how I did it, but you don't need to do that. You can say that it is the intersection of circle with AD, and then you have that SVK, that angle is equal to HMA, just because of the cyclic quadrilateral, and HMA is QTK, again by cyclic,
Using the cyclic one, yeah.
and that is STK.
Okay.
So SKTV is cyclic, and we can show that SKT is 90 degrees, I think. Yeah.
Okay.
Yeah.
So yeah, either way you can prove it however you define V. Okay. So we still have to show I. So we've shown we have that this is cyclic. We think we can use it to prove that this and this are each cyclic. And then it's still remaining to show that I lies on it, right? All right. Okay, so we have this.
I don't know if it works, but we can just state state the problem quite simple like this. So we need that TD and HK meets on the 9-point circle. It is just equivalent to saying that angle AKH is equal to DTM.
Okay, AKH is BTM.
Yeah, I mean it's that simple, but it's really hard to relate the line TD to calculate the angle. But we can just erase everything and just try to prove it that way. But I'm still working on it. So if you guys want to, you can just go that way.
Okay. Let me see if I can highlight those two angles. So I'll just draw like this. So it's just AKH and BTM. Whoops. Sorry.
It's DTM.
Oh, DTM, sorry. Yeah, that does seem like a lot simpler.
Yeah, it's simple, but it's not easy to prove. But I think we should, look things simpler. But still, there are many properties, nice properties around point like a V or L.
Okay. Stefan, what do you think? Do you want me to keep the circles, or I'll keep them for now, since I think Stefan had some ideas with it, but I'll try to look for that proof. AKH equals DTM.
Okay, I found another cyclic quadrilateral.
Okay.
Yet another. Q, I, H, and D.
UIHD.
And this is nice since then G. Oh, we.
You lies
Even
on.
better. Yeah, maybe that falls from immersion. Don't know. But okay, but that is nice since G would then lie on the radical axis of H, I, M, K, T and H, I, H, D.
The radical axis of H.
Yeah, basically we could maybe try some powerful point stuff if we knew those.
Okay, so like this. Yeah, we have two circles passing through H and U. And then we have this one. Yeah, so if we knew that this, and this, yeah, basically by the radical axis theorem, I think UH, MT, and Q, UH, MT, oh no, this doesn't pass through T. Oh man. UH, MK, and QI would concur. Yeah. So in other words, we might be able to show by the radical axis theorem that UH, MK, and QI concur. And then we'd have to show it lied on, yeah, OH. So yeah, AKH. I wonder if that's similar to some other triangle. I wonder if this point right here So anything special? You think there's any more cyclic quads here?
I think not a secret quad, but some more progress. Okay. Let's say we intersect Euler line with circle, the small circle QHD.
Okay.
So this is point U.
Okay.
Okay, now invert. Actually, not yet, but let me think. Yeah, also intersect EF with BC.
Okay. Oh, it looks like it lies on that circle.
It does, and that is easy to prove.
All right.
So we would basically have that U is the foot of perpendicular from Z to the Euler line.
Interesting. That's an easier.
That is easy. That is, this is, all of that is like, let's say, trivial.
Yeah.
Now invert at H with that power I said before, HA times HDE and negative inversion.
Correct.
Then Z would invert to Humpty point,
Okay.
to a Humpty point of, yeah.
Oh yeah. So I could just
Yeah.
draw that.
Okay, so since Humpty point lies on the median, I think this proves that AUDG is cyclic. I think.
Okay.
Since U inverts to some point on Euler line, Z inverts to A1, the Humpty point, and D inverts to A. So A1 and G, let's say G is the inversion, not the centroid. Then A1 and G are linear. And we know that G is on the Euler line, so G is the centroid.
Okay. So then G has to be the centroid.
Yeah, so I think now that this proves that QHD and AGD intersect on Euler line.
Okay. AGD. Okay. So it proves that this and this intersect on the Euler line, is what you're saying.
Yeah.
Okay. QHD. Okay. Yeah, it's okay. It's all about defining things in the right order. I don't think these concur, or maybe they. Yeah, let's see. Oh, it looks like these do concur right here. So EF, TL, and HM concur. Maybe that's obvious by the, yeah, that's might be obvious by the radical axis. Because yeah, if we have this circle, and this circle, yeah, by the radical axis theorem.
But keep in mind that we don't know everything that is cyclic.
Yeah.
Some things we don't know yet. So maybe proving that would help.
But yeah, I wonder if we could just define U to be the perpendicular from Z to the Euler line, and then we can prove everything from there. And then like that would eventually show that IH and K are collinear. Do we have enough to do that? So first we define U to be the perpendicular from Z to the Euler line. Then we'd want to show UH, M, K, T are cyclic. And B, I guess. UH, M, K, and B are cyclic. And then we could try to show that UDGA is cyclic. And then from there, once we show that, then that would prove that IH and M are collinear, or IH and K are collinear, right? So yeah, let me write this out.
Also, what I just figured out is that if we prove that I lies on that small circle QHD, then by the same that inversion, it would follow that IH and K are collinear.
Okay.
So proving that is very good if we knew how to do that.
I think it might be easiest to start. It's all about start by letting Z equal EF intersect BC. Then we know that A, Q, and Z are collinear. That's well known. That's another property of the Humpty point. I'm not sure if Johannes is still on. Yeah, he is. So yeah, let EF intersect BC at Z. A, Q, and Z are collinear, and then drop a perpendicular from Z to the Euler line. Then Z, U, Q, H, and D are cyclic. And then maybe we could like let it intersect this at point I, and then try to prove everything from there. Or maybe we could just let TD intersect it at I and try to prove everything from there. Yeah.
I think TD would be a bit easier, but I'm not sure.
Okay. So yeah, let's do it that way. Let TD intersect this at I. Intersect the small circle at I. So yeah, we don't know yet that I. So yeah, I'll start writing it out and see where it goes. All right. So let EF intersect BC at Z. Let U be the altitude from Z to OH. Then ZUHD, Z and Q, so A, Q, and Z are collinear. That's well known. It's on my channel in video 5, I think. linear, and that means that angle ZQH is 90. That means that ZUQHT is cyclic. And then let TD intersect this circle at I. Now we want to show that QIMKT is cyclic. And you did an angle chase before that, I think. I'm trying to remember.
For which one?
QIMKT.
Yeah, just for QMKT. I don't know for I yet.
Okay. All right. So we could start out with QMKT.
So we prove that TQM is equal to AKW.
Okay. TQM equals AKW.
And both of those angles are calculatable in terms of angles of ABC.
Okay, so angle TQM is angle SQM, which is SQA prime. Oh, so yeah, okay, I see it. So yeah, so angle TQM is SQA prime. And then SQA prime is going to be the same as AKW, since like this is a rectangle. So I'm just going to write that out for now. Yeah, so SQA prime equals AKW. That means QMKT is cyclic. Okay. And then now let's see if we can show I lies on it. So we know I lies on this circle. Can we also show, so so basically we define G as where the inversion takes Q, and then we show that A, G, and M are linear, I guess. So we might be able to show that this is cyclic that way. Well, basically we kind of define G to be cyclic, and then we show that G is the centroid. Because yeah, because Z goes to the Humpty point, which lies on the median. And so we want to show U also goes to a point that lies on the median. But since Q goes to M, yeah. So yeah, I think we can show, that this one is cyclic. fact, I wonder if that's just an angle change. So UDA is UDH is UZH is yeah, okay. So Z goes to A1 and U U goes to G and D goes to A. So yeah, so we can show that this one is cyclic too. I'll just write it out. So consider an inversion about H with radius HA times HD. So a radius square root that. So it swaps A and B. Let it take U to G prime. Then A G prime D Z A G prime B U is cyclic. And then G prime lies on OH. Okay, so it takes Z to A1 and D to A. Z to the A D point. And D to A. And Q to M. So basically this means that G prime lies on the A, both OH and the A median, and provides G prime equals G. Okay. So we've got that. Now, we want to show that this. Okay, so we just need to show that I lies on QMKT. Can we do that with an angle chase? So if we could show these concur, then we might be able to do it using like the converse of the radical axis theorem. But yeah, I'm not sure how easy that would be.
I think we should focus on proving that Q, H, I, and ID intersect on EF.
Okay, so yeah, showing they're concurrent.
Yeah, and by Rime's theorem, if we knew that, then we would know that I lies on that big circle QMK.
QMK, yeah.
Yeah.
TD, so we want to show TD, EF, and QM concur. Yeah, that doesn't seem like it should be that hard, but I don't know. Maybe it's trickier than it looks. That almost seems like it should be a well-known fact, right? TD, EF, and QM, because they're all well-known points, right? Like we don't even need Q, just TD, EF, and HM. I'm surprised I've never seen that fact before.
Yeah, me too. So I guess we could let TD and HM meet at a point, and then we want to show that lies on the polar of M. Oh, is that just true by a spiral similarity? Like, I don't think it's that easy actually. Well, if we hit TD for a second, if we let MQ meet EF at a point, then the ratio that point breaks EF into. Michael, sorry to
Yeah.
interrupt you, but I actually proved that part. So
Okay.
if you intersect, let's see, TD and HM, so we
Okay.
define it like that, you will need to prove that we have a harmonic bundle. So Q, that intersection point, we need to prove the concurrency point.
We have to show it lies on EF, right?
Yeah, but that would just be, it would be enough to show that Q, let's say B1, H and M are harmonic.
Okay.
Yeah, QB1, H and M are harmonic bundle, but that is actually very easy. You just project through T and cross ratio HS D infinity.
Okay. So
D is the midpoint of HS.
Okay, HSD infinity. Okay, so let me sorry, maximize just a tiny bit. Okay, so sorry, let me shift the whole page. Let HM, let MQ intersect D at B1.
And this is great. Now we actually also have that I, H, and K are collinear because we know that I lies on the big circle. So we proved the one part of the problem.
All right. So if we let HQ intersect TD at B1, then
also, sorry to interrupt you again, but you see that actually O is quite irrelevant in the problem. So could you just like hide that circle which passes through O and R and then and those stuff? Just to make picture a bit clearer. I mean, it is really messy right now.
Yeah, I agree. All right. So we project through T, and then that shows. Okay, so we wanted to show that what was it? Q, B1, H, and M is harmonic. Yeah. So projecting through T, projecting through T onto AB. We have QB1HM, or I could say QHB1M is equal to SHD infinity QY, and that's equal to -1. And that means that E, F, B1, and Z are collinear. Let me think about that a little bit.
Now HD and TM are parallel.
Okay.
And you can use Rime's theorem to prove that QI, MK, and T are cyclic.
Okay.
Basically, that I lies in the circle.
So I think it's right, because if we know they're collinear, then we know that B1I times BD is B1F times B1E, which is B1H times B1Q. So that's basically the same idea, right? Because basically it's like the reverse of the radical axis theorem. Like we know that B1Q times B1H is B1I times. Actually, what was I doing? I just confused myself. So we want to show this is cyclic. So B1I times B1T is B1Q times B1M. What were the three circles I had in mind? Oh no, this. Okay, so it's this one. Oh, but we don't know. Okay, so you're saying, okay, Rime's theorem, because MT and HT are parallel, by Rimes theorem, QIMT is cyclic. So HT is parallel to MT. QIMT is cyclic by Rimes theorem. Since QIHT was cyclic. Okay. And that shows that I, H, and K are collinear. So is that
So
that means
me
that
just-
I inverts to K, which means I, H, and K are collinear, right?
yeah. Just wait a minute.
Okay.
Have we made a mistake?
Where?
Do we know that I lies on the small circle?
So we defined I to be the intersection of TD with
9-point
small
circle.
circle, right?
Mhm. Maybe we made a mistake. Not in this part. We know that those three concur. That is all right, but the Rimes theorem thing.
For the Rimes theorem. Well,
Yeah.
QIHD is cyclic, and we know that, and we know that MT is parallel to HD. Oh, but
Yeah.
now, yeah, no, I think you're right. Like, so QHD is QMT, right? So
Yeah.
QHD is QMT, and QHD is also QID, which is QIT. So I think we're okay there.
Yeah, but you used that I lies on the small circle.
But the way I thought about it, let I is defined to be the intersection of TD with this small circle.
The small circle.
Yeah, the small one. That was how I was thinking about it. Maybe it's
That still makes some problems, I think. Then for the inversion part.
So okay, so then we don't know that I inverts to K, is what you're saying.
Not yet.
Okay.
Doesn't TD, EV, and QM concur mean QIMK and T are concyclic by power axis? And then I don't see where the mistake is if we define I to be the intersection of DT with the 9-point circle.
Oh, you defined I to be the intersection of TD with a 9-point circle.
Yeah, that collinearity of DT, EF, and QM gives us that QIMKT is cyclic, I think.
Okay.
Maybe. Yeah, powerful point, maybe somehow.
Okay, so we should define I the other way. So we could let TD intersect, because yeah, I don't think we use I anywhere here, right? So I could just say let TD intersect the 9-point circle. Circle at I. But then, and then you're saying we could use, if we define it that way, we could show QIMKT as cyclic. And how did you do that?
Like because we know EF, DT, and HM are collinear, so like I think that's just by power of a point.
Okay.
If they meet the converse of the radical axis theorem, like that should be concept.
Okay, so in that case, we don't know that this one is cyclic.
Yeah, I think he's all right, and also that he's correct. And we can also do power of a point to prove that I lies on the small circles. So we basically know what we thought that we know
Okay.
earlier. So you're all right.
Okay, so we have
You just say FB1 times you know,
B1E.
Yeah.
So we have FB1 times B1E is equal to QB1 times B1H. Or is that QB1 times B1H? And then yeah, wait, so how do we do it? So FB1 times B1E is QB1 times B1H. And then where do we go from there? Oh, and it's also FB1 times B1E, because it's a 9-point circle, that's IB1 times B1D. I guess, yeah, I'm trying to see how we use the radical axis theorem.
I got kind of confused too.
Right. Let's see. So we know this is cyclic, and we know this is cyclic. So it's okay. Since this is cyclic, it's equal to B1Q. And then this is cyclic, so it's equal to, so QIHD. Oh, so it means that QIHD is cyclic, basically. I think that's the idea. I think if we let these circles intersect at I prime, then I think we could just use the radical axis theorem. B1I.
It's easier just to do the power of a point directly instead of
Yeah,
defining another phantom point.
I agree. So I'm going to paste in what you just put. There we go. QIMTK is cyclic. So ID.
No,
No, we would-
QIHD, yeah.
QIHD UZ. And it's not Rhymes theorem, I know. Cyclic. Okay. And then we have I inverts to K. So
But first you need to write that Rhymes theorem for QIMKT, just like before.
Okay. So by Rhymes theorem, QIMKT is cyclic. So HT is parallel to MT. QIMKT is cyclic. So IH and K are collinear, so we know that part of the problem. And then now we want to show that Q, I, and G are collinear. All right. Let's try to make every little bit of room that I can here.
Okay, here is another thing I just found.